After a 1 mole sample of HI gas is placed into an evacuated 1-liter container at 700 Kelvin, the reaction represented occurs. 2 HI gas yields hydrogen gas plus iodine gas. The concentration of HI gas as a function of time is shown below. Part A asks to write the expression for the equilibrium constant, Kc, for the reaction. The equilibrium constant for concentration is equal to the concentration of the products over the concentration of the reactants, with any coefficients stated as exponents. For this reaction, Kc equals the concentration of hydrogen gas times the concentration of iodine gas over the concentration of HI gas squared, because in the balanced equation there are 2 HIs. Part B asks, what is the concentration of HI at equilibrium? We can solve this question by looking at the graph. A chemical reaction reaches equilibrium when the concentrations of the reactants and products do not change with time. On a graph, this looks like a straight line. So the concentration of HI at equilibrium is 0.8 molar because the concentration of HI remains constant at that concentration. Part C asks to determine the equilibrium concentrations of hydrogen gas and iodine gas. To solve this problem, I used an icebox. We are given that there is a 1 mole sample of HI placed into a 1-liter container, so that means there's 1 molar of HI, since 1 mole divided by 1 liter equals 1 molarity. That gives us the initial concentration of HI. You can also find this by looking on the graph. We know the equilibrium concentration of HI is 0.8, so we can plug that into the icebox. Next, we want to find the change. Since there's a coefficient 2 in front of HI in the balanced equation, the concentration decreased by 2x. Since we know the equilibrium concentration of HI, we can solve for x. The initial concentration of 1 minus 2x equals the equilibrium concentration of 0.8, so x equals 0.1. So that means the concentration of hydrogen gas and iodine gas changes by 0.1, but instead of decreasing like HI, it increases by x, so it increases by 0.1. Since the initial concentration of hydrogen gas and iodine gas are 0, the equilibrium concentration is the same as the change, so the equilibrium concentration of both gases is 0.1 molar. Part D asks, on the graph above, make a sketch that shows how the concentration of hydrogen gas changes as a function over time. From our previous calculations from Part C, we know the equilibrium concentration of hydrogen gas is 0.1 molar. So the concentration of hydrogen gas will remain constant at 0.1. The line will curve starting from 0 because at the start of the reaction, no products have been formed. The line curves up and remains constant at 0.1, which means once it reaches 0.1, it does not go above or below that line. Hydrogen gas reaches this point of equilibrium at the same time HI gas does, so at the second dash mark on the x-axis. Part E asks to calculate the value of the following equilibrium constants at 700 Kelvin, Kc and Kp. Kc, the equilibrium constant of concentration, equals the concentration of the products over the concentration of the reactants, with any coefficients in the chemical equation given or written as exponents. So Kc equals the concentration of hydrogen gas times the concentration of iodine gas over the concentration of HI gas squared, which equals 0.1 times 0.1 over 0.8 squared, which equals 0.016, and there is no units for Kc. To find Kp, I use the equation Kp equals Kc times R times T to the delta N power, where delta N equals the change of moles of the products minus the reactants. There's a total of 2 moles on the reactant side from 2 HI, and there's a total of 2 moles on the product side from hydrogen gas and iodine gas. So delta N equals 2 minus 2, which equals 0. So Kp equals Kc times the gas constant R, 0.0821, times 700, the temperature in Kelvin, to the 0 power. So Kp equals Kc times 1, since anything to the 0 power is just 1. So Kp equals Kc, and since Kc equals 0.016, Kp also equals 0.016. At 1000 Kelvin, the value of Kc for the reaction is 2.6 times 10 to the negative second. In an experiment, 0.75 moles of HI gas, 0.1 mole of hydrogen gas, and 0.5 moles of iodine gas are placed in a 1 liter container and are allowed to reach equilibrium at 1000 Kelvin. Determine which direction the reaction will need to shift to reach equilibrium, and whether the equilibrium concentration of HI will be greater than, equal to, or less than the initial concentration of HI. To solve this problem, I solved for the reaction quotients, Q, and then compared that to K to see which direction equilibrium would shift, or if the reaction was even at equilibrium. Q equals the initial concentration of the reactants over the initial concentration of the products. Since there is only 1 liter of solution, the number of moles of each substance is equal to the molarity of that substance. So Q equals 0.1 times 0.5 over 0.75 squared, which equals 8.9 times 10 to the negative second. So Q is greater than Kc, since Kc only equals 2.6 times 10 to the negative second. This means the system is not at equilibrium and will shift left, and will produce more reactants, therefore producing more HI. So the concentration of HI at equilibrium is greater than the initial concentration of HI.